Oh, hello there. Good to see you.
Bless you.
All right, so I guess I'll wait for a couple more people to show up. Oh, here we are. One more person. Okay, open participants. How's everything going? How's your weekend? It was all right. Who did something fun? Anybody? Even like one person?
I kind of did something fun. For soccer, we traveled up to
Lady,
the
I
bay.
think you're trying to tell me things. Oh, wait. Does everybody hear Delaney who's not me?
Yes.
Oh, there. Now I hear. Okay. Okay. Could you say it?
Now,
Yeah.
we traveled up to the bay and played St. Mary. I mean, we lost, but it was kind of nice just getting away from San Diego and change of scenery. It was refreshing.
Oh, yeah. I bet. Yeah. I would love to go up to the area. Well, sorry you lost, but I get it. Like, I think it'd be just getting out is good. Anyone get a COVID shot yet? Had 2 people in my other class who've gotten shots. If you're an employee, a USD employee, then you're eligible to do. Oh yeah, right. Annie has gotten them. Yep. any others of you who are USD employees are eligible to get shots. So keep that in mind. And I was sort of waiting for one more person. Go. Okay, I think what I'll do is I will make an announcement in a few minutes when another person shows up. But for now, I wanted to talk a little bit more about section 8. So section 8 is about permutations. Oh, I better share my screen before I just start writing it for a second. Okay, let me chat one back up. All right, okay, so everything's up. So it's about permutations, so section 8. And last time we found out why permutations were so important. And the reason that permutations were so important is, because of Cayley's theorem, which is that basically every group can be thought of as a group of permutations. So I'm just going to write these things down. There was one more thing I needed to say after Cayley's theorem, but we just raced through Cayley's theorem and then didn't have time to say it. So now I have to bring our brains back up to that same speed before I can say that last little piece. So recall Cayley's theorem is just says, every group is isomorphic to a group of permutations. Permutations is, all we have. Everything else is just window dressing, right? Everything else is just different names for things. But really what we have are permutations. And we had some detail about what that meant. So what's can you remind me what a permutation is?
A rearrangement.
Yeah, that's right. It's just a rearrangement. It's a shuffling of the elements. And then the official the math way to say that is it's a function, which is 1-to-1 and onto. So if we're thinking about this theorem, every group is isomorphic to a group of permutations. The way this theorem was proven is, think of a group G, take an element of G, and then try to think of a permutation that corresponds to that element. And the permutation we came up with was thinking about a row of the multiplication table for a group and sort of multiplying on the left. So I'll just remind you of some pieces of that. So for every X in G, G, where G is a group. We defined a function from G to G. Well, actually, it doesn't have to be a group for this part, but okay, fine. We find a function from G to G by, well, what does it do to an element of G? The answer is it takes that element of G and multiplies on the left by X. So this is a function, and you had an exercise over the weekend, which was to prove for lambda x above, show 1 to 1 and on to. In other words, it's a permutation. Okay, so this was our connection between x in a group and lambda x in permutations of that group. And phi, we defined phi to be that map, which associates an element of a group with a permutation of that group. Okay, so that's sort of getting where we were. Phi ended up, phi was the, we showed to prove Cayley's theorem, we just showed phi was homomorphism and 1 to 1. And then we know that it's, onto whatever it maps onto, it's onto its image. So it's isomorphic to whatever its image is in the group of permutations. So that was how that went. I wanted to say all that stuff because I wanted to give you one more or two more, I guess, definitions. So what this is this is a way to express any group that we're thinking of as a group of permutations. It's a way to translate. Let's suppose all we really like to deal with is permutations. Then we take some group that somebody else gives to us and we're like, I don't feel comfortable with that. I'm just going to translate it over to the world of permutations and do everything in the world of permutations that I know how to deal with. That process of translating, the way to express a group like that is called a representation. So you're representing any group as some group of permutations. So that's the definition. It's going to be kind of it's a vague definition, but I could be more careful about it, but I'm not. So a way to express a group as a subgroup of permutations is called a representation. This is how we're representing the group. This is the clothes we're asking it to put on. This is the perspective we're thinking of it from. Okay? Representation. And so this thing that we just talked about above is a representation. It's a way to represent this Cayley's, the details in Cayley's theorem gives a way to represent the group as a bunch of permutations. And in fact, there's a definition for that, which is the left regular representation. So let G be a group. Okay, let G be a group, then this function that we defined above from G to S sub G, given as we did above, what does phi do to some element X? Well, it produces the permutation associated with left multiplication by X as above. That function is called the left regular representation. So it's already a representation and it has a special name. It's the left regular representation. Left representation because, you know, we're multiplying on the left. Regular, I don't know, it's the standard one. I don't know why regular representation for reasons I just sort of described. And so you might not be surprised to think there's also a right regular representation. And it shouldn't surprise you that the right regular representation you multiply on the right rather than on the left. Let's think about this sort of pictorially. So first, the left regular representation. This is how the conversation started in the beginning. You know, we had some group, I don't know. Here's part of the group, let's just say. And we chose some element to be X. And we realized that if we looked at this part of the table, maybe, you know, B times E has to be B, but who knows, B times A. Maybe this is what the row looks like. Remember that, how did we get from here to here? Like, what does the multiplication table mean? How do we get from A to E? How do we get from B to C? How do we get from C to A? What was the activity that we did?
You left multiplied by the column.
That's multiplied by whatever element was in the column. That's right. So, and in fact, that's what gave us the permutation. So if these guys get shuffled to these guys, that was our lambdas of X. And we got there, you know, this element is A multiplied on the left by X, or A multiplied on the left by B. Okay, so that's the left regular representation as seen in the rows. Let's think about the right regular representation. Same group. Who knows how many of our elements are, but let's say, you know, B, E, that's going to be, that's be a B. I just made that up. Okay. So in this case, we're thinking of X as being this element and realizing that we're just multiplying E on the right by B, A on the right by B, B on the right by B, C on the right by B, to get those elements. So the right regular representation corresponds to the columns. Oops. These are the rows. These are the columns. Here's a question I didn't ask the other class, but let's just, because it just only occurred to me now. Are there any conditions where the left regular representation is the same as the right regular representation?
When the group is abelian?
Yeah, that's right. When the group's abelian, then it doesn't matter if you multiply left or right. We're gonna get the same thing. Another way to see it is the table, multiplication table of an abelian group is symmetric whenever you flip it across the diagonal. That would mean that the column is the same as the rows when you flip it across the diagonal. So yeah, okay. So sometimes they're the same, usually they're not. That's what I wanted to say about that. So what questions do you have about this part? Okay, so all that preamble was, I guess it's also probably good to just remind you of a very important theorem so that it sticks in your brain more. But also, I just wanted to give you this extra little piece of terminology. I also want to do one sort of example, sort of practice problem thing, just so you can get used to thinking of things from this new point of view. So let's consider this set G. Let's verify that these 6 matrices okay, so these are all 3 by 3 matrices. Verify that these 6 matrices form a group under matrix multiplication. I probably should have left some space so I can give them names. For now, let's just call them, this is the identity. Let's just give them names like this. Okay, there's at least 2 ways that we can do this. One way is just directly, which the way you've been sort of doing it forever. But what would that involve? Well, so let's see. We have to show closure. Closure means anytime you multiply 2 elements in the set together, you get another element in the set. So we'd have to multiply together 6 choices for the first, 6 choices for the second. So we have to multiply together 36 different products, matrix products, and then check to see if all 6 of them are in the list. It's not impossible, but that's kind of tedious. We could also, we'd also have to find the inverse for each one of these and show that it was in the set. And we've got the identity located. So this is totally possible to do. I want to do it a different way because it might be a little bit easier and it also sort of changes our perspective. So here's another option. Option 2 is let's just consider what happens to a column vector when left multiplied by these matrices. Okay, so let's see. Got the identity times 1, 2, 3. No surprise, that's just 1, 2, 3. I have A times 1, 2, 3. That's okay. What's A? 0, 1, 0, 0, 0, 1, 1, 0, 0. But what happens? So when we matrix multiply, this row gets multiplied by this column. So this time, the zeros aren't going to do anything. It's only the 1 that's going to do something. It's going to pick up this 2. This is in the middle location. It's going to pick up the term in the middle location here. So the first element is going to be a 2. Similarly, here, the first 2 are going to get multiplied by 0, but the third one's multiplied by 3. So this is only picking up the third element. So there's going to be a 3. And then for the last one, this thing is going to pick up 1, and each of these are multiplied by 0, so there's a 1 there. We can do this sort of thing for all the matrices. So B what does B look like? So B is going to pick up the third one, and then the first one, and then the second one. You can just do this multiplication yourself if you're not buying what I'm doing right here. Next, come back. So what does C do? C is 1, 0, 0. Oops. So the first one's going to pick up the first one. The second one's going to pick up the third one. That's what C does. D. Third, second, first. E. Second, first, third. Oops. Okay. This is what they all do. What does this have to do with this section? Why did I just do all this multiplication out?
Well, it looks like all of the resulting vectors are just permutations of the 1, 2, 3 vector.
Yeah, that's exactly right. That's exactly the right thing to recognize. The ending vector is just a permutation of the beginning vector each time. And so really multiplying by these matrices has the result of permuting the elements 1, 2, and 3. In fact, these are called permutation matrices. If you go back to linear algebra and look up permutation matrices in your book, you're going to find things like this. Okay, these are permutation matrices. Okay, and so this corresponds to a permutation. Well, this permutation, E is the identity. So that's just, 1, 2, 3 goes to 1, 2, 3. But this one corresponds to some A, which is 1, 2, 3 goes to 2, 3, 1, etc. So can you see how I can do that for all of them? So every element of the matrix corresponds to a permutation. Look how I've represented this set of matrices, all of them as I don't know if I just said partition, but I didn't mean that. I meant to say permutation. I just represented this set of matrices as permutations. So each matrix corresponds to a permutation. Of the set 1, 2, 3. And actually, but that doesn't mean it's a group. In some sense, what I've defined right now is a function, right? I have a function. This would be our phi, which connects elements of G with permutations. But how many different permutations of the numbers 1, 2, 3 are there?
6.
Yeah, there's 6 total. And hey, look, we've got 6 different ones right here. So we've got all of them. So in other words, if I translate over to the permutation world, I've got all of the permutations. So what group really is this isomorphic to?
S3.
S3, that's right. Since there are 6 different matrices, when I say different, I mean having different effects. Then it's got to be all of S3. With composition. And phi is the phi defined above sort of weakly here, which is, it's takes what you would expect, how it looks like it's permuting and turns it into that permutation. Phi is that connection. Okay, so if you just showed that phi, so to show that phi is a homomorphism one-to-one, you wouldn't even really need to show onto, but because since it has the right number, if it's onto, then it's one-to-one, or another, or alternately, if it's onto, if it's one-to-one, it has to be onto. But in any case, you can show these three things, and then you would know that by sort of Cayley's theorem that G is isomorphic to that. In other words, you really just have the group. So that would imply that G is a group. Anyways, it's a cute way to think about this, and not just a cute way, but one sort of goal. I was actually talking to another student about this a couple of days ago, and I really like thinking about this. To me, one goal of learning mathematics, it isn't as much, part of it is just learning problem solving in general, which I think is super good for everybody's brain. Part of it is also putting some structure on your brain, or maybe like putting a structure filter on the front of your brain, so that when you see things happening out in the world, you're like, oh, I understand that structure. That's really just a permutation of something. Do you know what I mean? Like you've got some understanding, some sort of base understanding from which to interpret things from. And that's super true of permutations. Permutations are everywhere. And you might start seeing them now. You might start seeing groups and things, and you might start being like, wow, look, how is that a permutation? You might be able to see those sorts of things. And then that might give you greater insight to how certain things behave. Okay, so that's my sermon on this. Anyone have any questions about this example? Or anything that we've said today, or anything we've said this entire semester, I guess? Let's just get weird. Nobody has any questions on anything the entire semester. We've all mastered it. That's awesome. Okay. I just wanted to make one. So while we're going to segue into a new topic, I just want to see is, yeah, so there a couple of your classmates got an awesome honor yesterday. Both Valerie and Hannah were invited to join Phi Beta Kappa, which is a very prestigious honor society. And so I'm just really proud of them, and I just wanted to congratulate them and like embarrass them in public, basically. So nice job, you two. It's an honor society, not just based on like being good at math, but being a well-rounded scholar. You know, being just strong in general, having breadth, and it's a real honor. So nice job on that. Yeah, so awesome work, guys.
Thank you.
Thanks.
Yeah, you guys are just, you deserve it totally. What great students. This is actually, look around. This is a pretty good class, right? Look at your friends. You're all in the company of greatness here, right? Look at all these. This is an amazing class. We're really lucky to have you, seriously. Okay, and now that I said that, I'm going to talk about some more math. Section 9, orbits, cycles, and the alternating groups. Okay, so I'm just going to start off with an example, and then because I've got a bunch of definitions to give you, and the definitions, reading the definition itself is like an exercise in frustration, but seeing an example of it and saying that's what I'm talking about, and then giving you the definition, would be like, oh, okay, that makes sense. So I just want to start with an example. So if I have this permutation, let's say sigma is an element of S8, permutation of 8 numbers that looks like this. So here's sigma. So let's see. 1 goes to 3, 8, 7, 4, 6, 5, 1, 2. Okay, perfectly good permutation. here's one way, here's another way you can represent it, and sort of one way to sort of think about things. So if you're just playing around and you don't really have a goal in mind, you might still have hit upon doing this. You'd be like, well, let's see, where does 1 go? If I apply sigma, 1 goes to 3. What if I apply sigma again? Actually, do you know about like fractals and stuff like that? Fractals and stuff is all about just iterating a function. Do it again and again and again and again. Iteration is such a common thing to do in math because, well, I don't know. I could get all weird, but you know, if you're like, what else do I do? Well, I'm just do it again, right? That's sort of a natural thing to do. So we do it again. So if I go to 3 and then I do it again, that means, you know, I put 3 back, I feed it back in, I feed the output back into the input, and then out comes a 7. And I take that output, I feed it back into the input, and out comes a 1. Oh, look, I got back where I started. So I can represent that as follows. I could say, well, let's see, 1 went to 3, 3 went to 7, 7 went to 1. So I'm closing this up. And I'm thinking of this as like, how should I describe this? I'm thinking of this as like kind of rotating around between them, right? 1 to 3 to 7 to 1 to 3 to 7 to 1 to 3 to 7. That's called a cycle. So this is an example of a cycle. But I haven't finished describing sigma yet. I've only just said, what does 1 do? So let's just see, what does 2 do? 2 goes to 8. And then if we apply sigma to 8, 8 goes back to 2. Okay, so 2 goes to 8, and then 8 goes back to 2. So we're done with that one. I could start with 3, but that would be dumb because I know what 3 does. I've already established it. 3 goes to 7, goes to 1 to 3 to 7 to 1. Why would I do this again? That's already right here. Right, we know where 3 goes, so I don't really need to even talk about 3. Or again, I've only already talked about once. What about 4? Oh, look, 4 goes to itself. So then if you do it again, it's going to go to itself and itself. Really, it just sits there, right? It doesn't do it. It doesn't go anywhere, no matter what. So 4 just goes to 4. That's all it does. It has a very stationary life. Five goes to 6, and 6 goes to 5. Is that it? Yeah, because 7, oh, that goes to 1. That's over here. Okay, 7 cycles on here. 8 goes to 2 to 8 to 2 to 8. Okay, so we've really got everybody handled. Each of these individual things is a cycle. And this activity that we just did, where we split sigma up the way we did, into cycles, that's called, that's called decomposing. We're decomposing sigma into a product of cycles. So this activity was decompose sigma into product of cycles. Okay. A cycle is really closely related to something that we call an orbit, except that an orbit is a set. An orbit is the set, and you have to say things like the orbit of a value of the group under a permutation. And so the idea is you take this element of the group, you apply the permutation, you apply it again, you apply it again, you apply it again, and then you just see, well, where all does it go? How far does it wander? What's its orbit? And then eventually it comes back. So an orbit is a set, it's just a set of all places where, the spaceship one visits on its tour, on the tour given by sigma. It gets on a sigma bus or on the sigma, I guess I should say, satellite or rocket ship, and it goes 1, 3, and 7. That's all it can do. But 2 gets taken over to 8, and then back and forth like that. And everybody has their own orbit. So the orbit is a set. So, but it's related. So for this one of the orbit of, let's say 3 under sigma is the set 1, 3, 7. Well, also the order of 1 under sigma is that same set, and the orbit of 3 and the orbit of 7 under sigma is also that same set. I just picked 3 so that you would know that it could be any of those that we picked. Okay, so the orbit is a set. Cycle kind of just a cycle is a function. A cycle says not only like here are the planets you get to visit, but here's the order one visits them in, and if you apply it to planet 1, it's going to take you to planet 2. Basically, that's what a cycle does. The orbit just says these are all the planets you can visit. This is on your itinerary. You know, decide how many times you want to jump on. Okay, so that's the difference. Now let me see if there's any questions about these ideas, and then I'm going to formalize them into theorems and definitions and stuff. Okay, this seems like it might be good. So here's some theorems and definitions. This thing that I just did above, you can always do. So each permutation sigma of a set A, I can always do this decomposition into cycles. I can always break it down into orbits. Let's think about the orbits for a second. This is going to, I hope, take you back in a very pleasant way to earlier in the class. The orbits, 1 and 3 and 7, they can, cruise around and visit each other, and that's it. 2 and 8 can cruise around and visit each other. 4 doesn't get to visit anybody. It's also like quarantine bubbles, right? All these guys, this is who they get to visit and who they don't get to visit. So, but if I consider the set of orbits as compared to the entire set 1 through 8, what have I done? What's the vocabulary word? Yeah, Jordan.
Is the orbit an equivalence relation?
Ooh, the orbit, you can define an equivalence relation based on the orbit. So the definition would be like, well, 2 elements are equivalent if and only if they're in the same orbit. So 1's equivalent to 3, 3 is equivalent to 7. 7 is not equivalent to 8. That sort of thing. Yeah, so you can't, and in fact, that is where we're going. But if I take the set 1 through 8, what's the flip side of that?
Do they form a partition?
Yeah, it's a partition. So I'm taking the set 1 through 8 and I'm partitioning it into its orbits. Okay, so each permutation of a set A defines a natural partition of A. Into cells. And so how do I decide, sort of based on in the cells called orbits? And so let me just define what that is. Okay, so if I have an element of A and a permutation of A, then the orbit of A under sigma, you have to specify the A and the sigma. So this is the thing that we're defining is, well, it's a set. So it's denoted orbit of A under sigma. And it's the set of all, what do? You take A and you apply sigma to it. How many times? Well, you can apply it again and again and again and again and again, any number of times. So it's in slang, it's all the elements of A that little a visits under repeated applications of sigma. Okay, that's the orbit. And then related to that, the orbits of sigma that's just all the orbits of all the elements of A. So if you don't specify a particular element, you just say orbits in general, it's sort of the set of all the orbits. So back to this example, which I don't really have room for, all the orbits are, well, there's 1, 3, 7, and there's also 2, 8, and there's also 4, and there's also 5, 6. Those are the orbits. It's the partition. Okay. Now, to put it in the terminology that Jordan was using, and we already know from what we talked about at the beginning of class, is that the flip side of every partition is an equivalence relation. So let's just talk about the same thing in terms of equivalence relations. So in other words, so here's a note. On the flip side, in terms of equivalence relations, let's see, if we define, I think I want to just call this equivalence relations, just so when you're looking at your notes later on, you know what section we're talking about. So from the other point of view, define for every A, B, and B, sorry, A, B, and A, define A to be related to B if and only if, well, they're related if they're in the same orbit. The orbit's the partition. The set of orbits is the way to partition the set. So the orbits are the cells of the partition. And you know the way you get an equivalence relation out of that is you say the two things are related if they're in the same cell, if they're in the same orbit together. So I'm going to say if and only if they're in the same orbit, but let's be specific. What does it mean to be in the same orbit? That means you can get from one to the other by repeatedly applying sigma. Okay, so if and only if there exists an n, a number of times you can apply sigma. So that sigma to the n of A is B. If you look at this description above, that's what it means to say they're both in the same orbit, right? If B is in here, that means B looks like one of these sigma to the n power of A's. Okay, so that's a relation, and I think a good exercise for you for homework and practice, show that this relation is an equivalence relation. Of course it is, because of the theorem and the fact that each partition gives rise to an equivalence relation. So of course it is, but proving it directly can help you just get more comfortable with the notation and the meaning and that sort of thing. Okay, so that's orbits. Notice I also named cycles. So let's talk about cycles now. Here's a definition that's going to be confusing. Permutation in SN is a cycle if it has at most one orbit containing more than one element. This is kind of a mindful. Contains at most one, if it has at most one orbit containing more than one element. So if I look up at here, this right here, the set just containing four, maybe I should look right here. This right here is a set containing just one element, an orbit with just one element in it. It's not going anywhere. It's not contributing to the activity of sigma. So we're discounting those. When we're talking about cycles, we don't care about the orbits that have only one element. Nothing's happening to them. We care about where the action is, where stuff's moving around. Okay, so this is saying that if we forget about these ones that aren't doing anything at all, there's at most one other orbit. Okay, so this thing, sigma itself, is not a cycle. Because look, here's three orbits. Here's three orbits containing more than one element. But any of these pieces individually, these are cycles. Because if I forget about the existence of any of this stuff, and I only look at this first piece, that first piece contains at most one cycle, at most one orbit with more than one element. Okay, so each of those individually are cycles, taken together, not a cycle. Okay, so sigma is not a cycle. Cycle should remind you of cyclic group, right? A cyclic group is where you sort of start with something, then you apply, and then you just go back, you end up where you started after repeatedly applying something. Well, now instead of just multiplying it by itself, we're applying sigma to it over and over, but still we sort of cycle around. Okay, so that's what a cycle is. And by the way, the length of a cycle is the number of elements in its largest orbit. This phrase, in its largest orbit, is, slightly ridiculous. Because in a cycle, there's only one orbit that has more than one element. So the largest is kind of like the only useful orbit, is what should be said by the largest, right? All the rest of them are orbits of size 1. And then there's one of them that's of size not equal to 1. And that's the thing that we're counting the length of. So the cycle 137 has length 3. But also, so if tau equals that, And if, let's say, omega equals 1, 3, 7, and then also 4, and also 2, and also 5, and also 6, still has length 3. In fact, I would say that sigma and tau are really the same thing. Because sigma isn't saying, it's not doing anything to any of the other ones. Sorry, I said that wrong. Tau and omega aren't doing anything to any of the other ones. Okay, so they both have length 3. Okay, so that's why I said above, we're thinking of sigma as a product. We decomposed sigma into a product of cycles. Cycle of length 3, of length 2, of length 1, of length 2. Okay. You can always do this. You can always split up a permutation into cycles like this. Because you just do what I just did. Just follow your nose until you get back to where you started. And how do you know? Okay, sorry. If it's a finite permutation, if it's a permutation of an infinite group, that's a different story. But let's just stick with finite. It's a permutation of a finite number of things. You can always do this. You just start with one, keep going until its orbit closes off. It has to close off because the group is finite. You can't go more than finitely many places. At some point, you get back where you started, close that off. If that's not everything, pick something else that's not in that orbit, see where that goes. And then you just keep until you get all of it. Okay, so you can always do this. And in fact, when you do, I don't know if you can predict this, or maybe since you've read ahead, maybe you can know where I'm going. What's true about these cycles and how they're related to one another? Or what's true about these orbits and how they're related to one another? It's maybe too vague of a question.
Are they cyclic subgroups?
There is a that's a complicated question. That's a deep question to ask and complicated to answer. So on one hand, it's not a group at all because because it depends on what you're talking about. The elements themselves, 1, 3, and 7, are elements of a set 1 through 8 where we don't have group structure necessarily that we're talking about. So in that sense, it's not a cyclic subgroup. But if you define it as like, yeah, and I guess powers of sigma. Yeah, that's related to. Yeah, okay. I guess if you're thinking, if you just pick that cycle and call that cycle tau or something like that, then tau generates a cyclic subgroup. Like that. Yeah, so there's a way to think about that. Yes, absolutely. That's true. And I was trying to ask something in a slightly different direction, but it's so vague what I'm asking, it's hard to figure out how to answer it. So let me just say, there's not going to be any overlap. These are going to be disjoint. All of them are going to be disjoint. How do I know that they're disjoint? If there was a 3 in here and also a 3 in here, the fact that the 3 is in here means the 7 has to be in here. And the fact that the 3 is in here means the 7 also has to be in there. And then the fact that the 7's in here means the 1 has to be in here. Same thing for here. They're just going to be the same. You're just going to, the fact, basically left cancellation forces you, once you meet, you have to be the same. So you're either going to be the same or 100% different. There's no overlap. Okay, so this theorem says, every permutation sigma is or can be decomposed into, wait, let's see if we find it set. Can be decomposed into or is, your book says is, a product of disjoint cycles. Here's why disjoint. Here's why the disjoint part of this statement is interesting. Or let me just say, disjoint is interesting in general, maybe not as applied to this particular theorem, but disjoint cycles commute. Cycles in general do not commute. Why do cycles in general not commute? Well, a cycle, really is just a permutation. A permutation is a function. The permutations are combined by function composition. We know that function composition isn't commutative. Cycles don't commute. Disjoint ones, however, it's like, think about trying to combine two functions. The first function like messes with 1 and 3. The second, but leaves everybody else alone. And the second function messes with 6 and 7, leaves everybody else alone. It doesn't matter if you switch 1 and 3 and then later switch 6 and 7, or you switch 6 and 7 and switch 1 and 3. The fact that everybody else is being left alone means it doesn't matter what order you do it in. So that's a heuristic reason why disjoint cycles commute. All right, there's a lot more to say on this subject, but I think what I'd like to do right now is just, pause, take a breath, find our center, see if there's any questions. Not quite